In this lecture, we'll continue to solve some problems. Given some circuit and some resistors or inductors or capacitors in the circuit, we saw how to analyze that during the lectures of Fourier transforms. Now, how do we use Laplace transform to do this analysis? It's very similar. We're going to start with the voltage current relationships, just like what we did in the Fourier transform case. And then instead of applying Fourier transform on both sides, we're going to simply apply Laplace transform. So if you take the resistor relationship, this is what we have, the relationship between the voltage and the current, and this is the capacitor case, this is the inductor case. Now we just apply the Laplace transform on both sides, then we get that the voltage across the resistor in the Laplace domain is simply equal to the resistance value times the current through the resistor in the Laplace domain, and similarly the case for capacitance and inductance. The nice thing here is that, so this integral operation simply now becomes just 1 by s because of the property of Laplace transform, and the derivative operation simply becomes multiplied with s because once again of the Laplace transform properties. So now things become very simple. Now what are we going to do is something very similar to the previous case. We are now going to simply say the voltage across some impedance in the s domain is equal to the impedance times the current through that impedance. Now this impedance is a generic term. It can model a resistor, it can model a capacitor, or it can model an inductor. So the way that we are going to represent the impedance in the Laplace domain is slightly different from what we did in the Fourier domain. In the Fourier domain, we simply said it is some a plus j omega or a plus some b, where b could be a function of omega. Now what we'll do here is we'll just say that this impedance in the Laplace domain is actually some a plus b divided by s plus c times s. Now, how would this help us model different kind of passive devices? So, if it was a resistor, then basically we are supposed to get just a constant, which means this b and c are equal to 0. Only this a is a non-zero number. Now, if it was, let's say, a capacitor, then we are supposed to get 1 by cs here, which means this is the only term that we are supposed to have, the other terms will go to 0. So for a capacitor, we have that a and c should be equal to 0 and b should be greater than 0. So this is capacitive and this is inductive. Right, so because for the case of inductance, we have just L times S, which means we are supposed to have only this term non-zero, the other term should go to 0. So one thing to keep in mind is all these terms are positive. A, B and C, whenever they exist, they should be positive term because we cannot have a resistor or capacitor or an inductor which is negative. Right? So all these terms have to be positive when they exist. So this can model an inductor or a capacitor or a resistor or any combination of them in series. So if you have both R and L and C, all of them in series, then the equivalent impedance would simply be Z equals R plus Ls plus 1 by Cs. Okay. So in this case, A equals R, C equals L, and small c equals L, and B equals 1 by capital C. So this is a simple way to model the elements in a circuit. Now let's solve some problem with this tool. So let's take a circuit which simply has two elements in series, and let us say that there is some x of t as the input, and let's consider this as the output. Let's try and find out the transfer function of this system and also from there the impulse response. So remember how we started out with solving RC circuits. Now we have taken a circuit which is very general, not just R and C. This Z1 and Z2 can be anything, and still we'll be able to easily analyze this. Just for an RC, we took so much time to analyze it at the beginning of this course. Now we are not saying what is this, it can be R, it can be L or C, whatever it is, and still we'll be able to solve this in a very quick manner. Let's see how to solve this. Laplace transform, you get x of s equals Z1 times I of s. Now remember, this Z1 is actually in the S domain. So this Z1 and Z2 that we have here are in the S domain. So I of S, we'll just simply replace this with Y of S because that's our output. Now, how do we get rid of this I of S? We know that Y of S is equal to Z2 times I of S. Because of this relationship, we can simply replace this I of S here as Y of S divided by Z2. So, in other words, the transfer function H of S is equal to Y of S divided by X of S, which in this case is nothing but, so we can simplify this as 1 plus Z1 by Z2 times Y of S. So, our transfer function would be now 1 by 1 plus Z1 by Z2, which is equal to Z2 by Z1 plus Z2. So, this is our transfer function. So, we got the transfer function in such a simple and an easy manner, right? So, now let us say this Z1 is equal to A1 plus B1 divided by S plus C1S. So, this is the most generic form of the impedance that we can have, and this Z2 is A2 plus B2 by S plus C2 by C2 times S. So, substituting that here, what do we have? So, we have here A2 plus B2 divided by S plus C2S times A1 plus A2 plus B1 plus B2 divided by S plus, or in other words, you can just simplify this equation as C1 plus C2 S square plus A1 plus A2S plus B1 plus B2. Basically, we are just multiplying and dividing by S everywhere, and you get C2 S square plus A2S plus B2. Now, if you just find the roots of the numerator and the denominator and simply take the partial fraction solutions, then you would be able to find out what is the impulse response. So, the impulse response H of t, how do we find the impulse response? Once again, use the relationship that 1 by S plus A actually has an inverse Laplace transform e power minus at u of t. So, this is a relationship that we are going to use. Well, let's take an example. So, in this case, we found out the most generic form of the transfer function. Now, let's take an example. What if this was R and this was C? Now, you can change this to L and C, whatever you want. Now, we'll just take R and C so that we'll just compare with what we got earlier. So, if this was R, then for Z1 equals to a resistor, we have that B1 equal to C1 equal to 0, and for Z2 equal to a capacitor, we have A2 equals C2 equals to 0. Okay. So, substituting that back, we have H of S to be equal to A2 is 0, C2 is 0, we'll just get B2, all right, divided by, and what will be B2 actually? B2 here will be 1 by capital C, and in this case A1 is equal to capital R, and C1 plus C2, both C1 and C2 are 0, so this term is 0. A1 plus A2, what is A1? A1 is capital R, A2 is 0, so we have capital R S, and V1 is equal to 0, B2 is 1 by C. So, dividing this entire expression by 1 by C, what would you get? You would get, so you can multiply in the numerator by C, and the denominator also you can multiply by C. So, basically multiplying and dividing by C, you get RCS plus 1, which is exactly the equation that we got earlier. So, if you want to write it in the form of 1 by S plus A, so once again what you do, you just take R common, then you get S plus 1 by RC, and in the numerator you get 1 by RC. So, Now from this you can take inverse Laplace transform. And if you take the inverse Laplace transform, what is the transfer function? It's e power minus RCT u of t. Right? This is exactly what we got earlier also. So now this is a very nice generic expression. This is quite nice. You can plug in any impedance that you want. You can even have a combination of impedances here. So you can have a resistor and an inductor here. You can have a capacitor and another resistor here. So you can have any combinations in series, and then still the same equation will model everything. So we have gotten one equation which can model all possible combinations of impedances, and still you will be able to find out what is the transfer function and the impulse response like this. So this is the power of Laplace transform. So not only to analyze a system, but also to design a system, it could be useful. So let us see how this is useful in design now in this example. So the question is, some transfer function is already given to you. So h of s is given to be 1 by a s square plus b s plus c. Okay, so if this is the transfer function that is given to you, how do you analyze this system? So first, what are the poles and zeros of this system? What are the zeros? It does not have any zero. That's great. So it has only poles. And what are the poles of this system? Basically the roots of this equation. So what are the roots of this equation? The roots of this equation are simply nothing but minus b plus or minus root of b square minus 4ac by 2a. So those are the two solutions of this quadratic equation, and these are the poles. So we have two poles here. Okay. So if we have to draw, so there could be two possible cases, that if the poles are all real, then what can we have? So we can possibly have something like this. We might have poles like this, or we can have a repeated pole, which means the pole can exist twice, or we can have complex conjugates. So if there are complex conjugates, then probably we can have something like this, or we can have something like this, or something like this. So these are the possible cases. Either we can have purely real poles, or we can have complex conjugates as poles. So let us take one case. Let's assume that the most generic case, that the poles are some a plus or alpha plus j beta and alpha minus j beta. This is the most generic case of our possible poles here. So let us say these are the poles. How would the ROC look like? Now this is simple to answer in this case, because we are going to say that this transfer function corresponds to a circuit. If it corresponds to a circuit, it is a practical system, and for that reason this has to be a causal system. If it is a causal system, we know that the poles are going to determine the ROC. How? The ROC is the right of the rightmost pole. So we can just simply take this line and then say that the ROC is the right of the rightmost pole. So this will be our ROC. So this is the pole 0 plot. Okay. For a practical system, if this corresponds to a circuit, then this is how our pole 0 plot and the ROC will look like. From this, obviously we can find what will be the transfer function. How do you find the transfer function? If these are, let's say, d1 and d2, then the transfer function is simply nothing but e power d1t u of t plus e power d2t u of t. Okay. And that's all. That's the transfer function. So the entire circuit, if the transfer function is given to you, we can so easily analyze this and then say what happens to this system. So is the system stable? How will you say if the circuit is stable or not? The circuit can be stable only if the poles are all on the left side of the S-plane. Okay, so that's the condition, remember. So the poles, if they're all on the left half of the S-plane, then the system is stable. So for that to be stable, this alpha value, it should be negative. If that is negative, then you are safe, then your system is stable. Now there is a very particular class of filters called as Butterworth filter. So this can be used for designing low pass filters. So remember, we started out with discussing about how to design equalizer circuits. Basically, you want to design filters. So if I want to design a filter, let's say I want to design low pass filter, and my cutoff frequency is given by this omega c, let us say. So a Butterworth filter is a class of low pass filters whose transfer functions will be of the form h of s be equal to omega c square divided by s square plus root 2 omega c s plus omega c square. So this is what is called as a second order Butterworth filter, because here we have two poles. That's why it's called a second order Butterworth filter. Now basically it will have something like this. So you have in the Bode plot, you have, let's say you design something like this. Then you have a flat region, and at omega c, which is the cutoff frequency, then there is a steep fall. So why is there a steep fall? Because this is the cutoff frequency. At that point you see a pole, and after that there is a fall. So this is what a low pass filter looks like, and this is what we refer to as Butterworth filter. Now let us say you want to implement something like this. Then how do you find out the corresponding resistor and capacitor values? Now this is where our generic analysis comes into picture. So remember, we said this is how any RC circuit or any circuit which has two impedances in series is going to look like. Now if I want to implement a Butterworth filter with such a circuit, what would be Z1 and Z2? So in other words, we have to equate this to the equation that we have here. So this is C2S square plus A2S plus B2 divided by C1 plus C2S square plus A1 plus A2S plus B1 plus B2. So just compare the numerator here and here. So clearly the numerator says that B2 is equal to omega c square, and the denominator says that, and also we can get that A2 equals C2 equals 0, and from the denominator you can say that C1 is equal to 1 and A1 is equal to root 2 omega c, and once again, since B1 plus B2 is equal to omega c square, where B2 is already omega c square, you can see that B1 is equal to 0. So this is one possible choice. So this is not the only possible choice, this is one possible choice. So if this is one possible choice, then what are the components? Let's talk about this component. What is Z2 first? Z2, A2 is 0, C2 is 0, and B is the only term which is non-zero, which makes this a capacitor. So we have to have a capacitor here such that C is 1 by B2, right? The capacitance value is 1 by B2, which is 1 by omega c square, okay? And then what should we have here? So we should have here something which has A1 and a C1 component. A1 corresponds to a resistor, so we should have a resistor here, and we should have an inductor here. So the resistor should have a value of root 2 omega c ohms, and there is an inductor of 1 Henry here. So if you can construct this circuit, you have essentially constructed a second order Butterworth filter, which has a frequency response at a cutoff frequency omega. So this is a very nice and simple way of designing filters. So it's not at all complicated. If I want to design a filter, all I need to know is I need to know this transfer function or frequency response on Bode plot. So once you know that, you know where the poles should be, where the zero should be. Once you know that, you can write this equation. Once you know this equation, you know how to map it to any generic circuit like this. So if you have multiple components, if you have another component here, or if you have another component here, in a similar fashion you can analyze this, write the transfer function, you can get a very generic transfer function, and you can map these two polynomials, numerator polynomial, denominator polynomial, find out the coefficients like this, and from there you can find out what should be the value of the resistors or capacitor or the inductors that you have to plug in to get the desired filter. So this is a very simple and a nice tool to design filters. So we can design your equalizers like this.